Hi everyone. What's up? How are you all? Doing good? Yes, I'm also doing good. Yeah, really great. So, we've already completed few parts of the first chapter of chemistry. That is some basic concepts of chemistry, and we have reached in the problem 1.1 of NCRT textbook. We have done the problem in our last class, right? Hope all the sessions were easier till now, and the coming sections will also be easier to all of you, I'm sure. Okay, paka, paka, paka. Promise. Okay, so work in unity because unity is strength. You've heard about that, right? Unity is strength. So have group discussions, learn with your friends, teach them, and also take lessons from your friends. Like combined study will help you a lot. I don't know, but in my case combined study is somewhat helpful, but in some cases it's a flop, it's a failure. So think wisely and decide whether combined study is good for you or not, so that if it's good, yeah, definitely go for it. Find a right person to teach you or to discuss things mutually. That will benefit you for sure. So in today's class, first of all, let me tell you, in last class I told you about the U, right? Here, 180 U, unified mass, or it can be written as AMU. The unit is U, unified mass, or AMU, okay, atomic mass unit. So today I'm going to tell you a small short story about the origin of U, the unit U, or the atomic mass unit AMU. How it has come. Fine. You might have not seen this, but this is a weighing machine of stones, not a digital one. Okay, not a digital weighing machine. The other one, you might have gone to the grocery shop and you might have seen the shopkeeper placing things in one pan and placing weight in the other pan, 1 kg weight, 500 grams weight, right? You've gone to some shops. I think it's not much popular these days, but it was commonly used in 2000, all those days, 2000 year, 2001, 2002. In those days, this type of weighing machine was in common. Okay, so take a weighing machine like this. Place C12 atom, C12 atom, C12. I'll change the color. C12 atom. Okay, place C12 atom here. I'm also placing a C12 atom here. What is C12? C12. C12 means an isotope of carbon. You know what is isotope, right? I've already discussed what isotopes are, so I don't have to detail it now. So C12, I'm placing C12 isotope in one pan. I am also keeping C12 isotope in the other pan, right? So it will be balanced. C12 isotope in both pans means it will be balanced. Okay, now what I'm doing is I'm taking the same weighing pan. In the left side, I'm placing C12 isotope. In the right side, what I'm doing is I'm just equally dividing the C12 isotope or C12 atom into 12 units, 12 equal units. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Will it be balanced? Yes, of course it will be balanced because the C12 isotope is in left pan, C12 isotope is in the right pan itself, but it has been divided into 12 units. No difference. Now, the case is changing a bit. I'm placing the same C12, sorry. I'm placing oxygen atom here. Oxygen atom. I'm placing oxygen atom in the left pan. Will I require the 12 units of C12 isotope? Or I need more? Or less? Or the same C12 isotope is enough to balance the oxygen atom in the left pan? Think and answer me. Will I require the same C12 isotope, 12 units of C12 isotope to balance oxygen? Or I need more amount of the units there? Or less amount? I've divided C12 into 12 units, right? Should I need the 12 units to balance oxygen atom in the left pan? Or should I need more units of C12 isotope to balance the oxygen atom in the left pan? Yes, I need 4 more units to balance oxygen atom in the left pan. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay? Is that clear? So I've balanced the oxygen atom in the left pan with 16 units in the right pan. Is that clear? Now, I'm changing the case. I'm changing the same pan. I'm taking the same pan. In the left side, I'm keeping nitrogen atom. So think, how much do I require? 12 units, 13 units, 14 units, 15 or 16 units in the right side to balance the nitrogen atom in the left. Yes, 14 units. I need 14 units. 14 units to balance nitrogen in the left pan. So I'm not counting it, just randomly. 14 units is required. So C12 is balanced with 12 units, right? 12 units of C12 isotope. So I can say it, the mass of C12 isotope is 12 unit. C12 atom is 12 unit. So what's the mass of oxygen from here? I've used 16 units, right? So 16U is the mass of oxygen. In the case of nitrogen, I've used 14 units, right? 14 units. So the mass of nitrogen atom is 14U. 14U. Is that clear? So what is U, or unified mass? Or what is AMU, or atomic mass unit? I'll tell you. So here I've divided the C12 isotope. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, this is a pan. In the pan, I have 12 units of C12 isotope. In this, 1 unit of C12 isotope is called 1 AMU, or 1U. Means 1 by 12th mass of C12 atom or C12 isotope is called 1 AMU or 1U, 1 unified mass. I've divided the C12 isotope into 12 units. 1 unit, the mass of 1 unit is called 1 unified mass or 1 AMU. Means 1 by 12th mass of C12 atom. So you may be asked to define AMU or unified mass. Just give this answer. It is the 1 by 12th mass of C12 isotope. C12 isotope. Hope that's clear. Now, we need to know what is mole concept and molar mass. You might have gone to fancy shops to buy bangles, right? So, you might have told the shopkeeper that I need a dozen bangle. A dozen bangle. What does a dozen bangle mean? It means 12 bangles, right? 12 bangles. A dozen means 12. That's what I mentioned here. A dozen means 12. What a pair means? A pair of shoes. A pair of earrings. What does it mean? It means 2, right? A pair means 2. A dozen means 12. Likewise, score is also used, 20. Score means 20. Just leave score. You might not be familiar with the word score. But a pair of shoes, you are very familiar with that word. A pair means 2, right? 2 numbers. Means 2 quantity. The quantity is 2, right? A pair of earrings means I have 2 earrings. A pair of shoes means I have 2 shoes. Likewise, a dozen of bangle means 12 bangles. In the similar way, to represent the microscopic molecules, microscopic atoms, or the quantities at microscopic level, I have the term mole. 1 mole means 6.022 into 10 raised to 23. All the macroscopic objects are said like dozen, pair, score, etc., right? 12 means dozen, 2 means pair, 20 means score. Similarly, at the microscopic level, I use the term mole to represent 6.022 into 10 raised to 23 particles. If you go to a chocolate shop and you see 6.022 into 10 raised to 23 chocolates in the shop, you can proudly say that the shop has 1 mole of chocolates. Hope it's clear. Fine. You've gone to a chocolate shop, you're seeing 6.022 in 10 raised to 23 chocolates in the shop. You can definitely say that the shop has 1 mole of chocolates. Fine. To express the quantities at microscopic level, we use the term mole, which means 6.022 into 10 raised to 23 particles. And this can be said as Avogadro number. This number is called Avogadro number. The number of 12 is called what? Dozen. The number of 2 is called pair. The number of 20 is called score. Similarly, the number of 6.022 in 10 raised to 23 is called a mole, an Avogadro number at the microscopic level. And it's represented as Na. Na. Fine? Is that clear? Okay. Now, tell me the mass of one oxygen atom. Tell me the mass of one oxygen atom. One oxygen atom. What's a mass? 16 grams? No, it's not 16 grams. Yeah, I heard someone saying the right answer. There. Yes, it's 16U. It's 16U. The mass of one oxygen atom is 16U. Then what is 16 gram? The mass of 6.022 into 10 raised to 23 oxygen atoms is 16 gram. 1 mole of oxygen atoms means it has 16 gram. 1 oxygen atom means it has the mass of 16U. Similarly, in the case of, we'll take maybe nitrogen. What is the mass of 1 nitrogen atom? What's the mass of 1 nitrogen atom? It is 14U. The mass of Avogadro number of nitrogen atoms. The mass of Avogadro number of nitrogen atoms equal to 14 gram. So whenever you're asked to say the mass of one atom of something, you need to express it in U. And if you're asked to express the mass of something, 1 mole of something, you need to express it in grams. Okay? Now, you already know what is mole. So we need to find the number of moles in a specific component. We have 4 different equations to find number of moles of something, which this is usually asked in numerical problems. You're asked to find number of moles of this, that, etc., etc., etc. So you need to know 4 basic equations to find the number of moles. Okay, and it's given here, number of moles equal to given mass by atomic mass. Given mass by atomic mass. For example, you are provided with 32 grams of oxygen. 32 grams of oxygen. Okay, so the given mass can be divided by its atomic mass 16. That is equal to 2. So the number of moles is 2. Number of moles is 2. So that's given here, given mass divided by atomic mass. Hope the equation is clear. The next equation is number of moles equal to given mass by molar mass or molecular mass. So you're provided with 18 grams of water, H2O. So you are asked to find the number of moles in this substance, water. So is water an atom? No, it's a molecule, right? It's a molecule. It's a mixture of hydrogen and oxygen. So you're not able to use the equation of given mass by atomic mass, but instead you need to use the equation of given mass by molecular mass. Given mass by molecular mass. So the given mass is 18 grams. The given mass is 18 grams. You need to divide it by the molecular mass of water. What is the molecular mass of water? Hydrogen 2 plus 16 of oxygen gives 18 itself. So 18 divided by 18, 1 mole. Okay. Now we are moving on to the third equation. Number of moles equal to number of particles divided by Avogadro number. Number of particles divided by Avogadro number. You know what is Avogadro number? Na equal to 6.022 into 10 raised to 23. Okay, you're provided with somewhat 18 point something something. Okay, 18 point something into 10 raised to 23. You're asked to find the number of particles in that component. You just have to do is that you just have to divide this number of particles by 6.022 into 10 raised to 23. You'll get approximately Na 3 moles. 3 moles. If you are provided with the number of moles, number of particles in a component, in a substance, you just have to divide it by Avogadro number, that is 6.022 in 10 raised to 23. You need to by heart the value of Avogadro number. In some cases, you won't be provided with the exact value of Avogadro number. Now comes the fourth equation, the last equation to find the number of moles in a given substance. Number of moles equal to volume of gas at STP divided by 22.4 liters. This equation can only be done at the case of STP. STP means standard temperature and pressure condition. Standard temperature, you have learned about the STP condition in 10th, 9th I guess. So standard temperature and pressure condition means at 273 Kelvin temperature, pressure 1 atm, number of moles of a substance 1, you have the volume of that substance which is equal to 22.4 liters. This is the standard temperature and pressure condition. At 273 Kelvin temperature, 1 atm pressure, at 1 mole of something, you have 22.4 liters of that substance at STP. You can say like that. What if I'm provided with 2 moles? 2 moles. Instead of 1, I'm provided with 2 moles. What will happen for the volume, to the volume? Will the 22.4 remain same? No, it won't. It will change to 44.8, right? Yeah, 44.8 liters. So at STP, if you have 2 moles, the volume will be 44.8. If you have 1 mole, you will have 22.4 liters. As the number of moles increases, the number of the volume will increase. Okay, will be the multiple of 22.4 liters. So if a question is given like this, at STP, the volume of a gas is maybe 44.8 liters. You're asked to find the number of moles of that species. You just have to divide it by 22.4 liters, which is a standard temperature and pressure condition volume. The volume at STP, you'll get 2 moles. 2 moles. All set? Now we are moving on to the question answer section of today's part. Give the Avogadro's number. What is Avogadro's number? 6.022 into 10 raised to 23. Alright. The mass of 2 moles of ammonia gas. 2 moles of ammonia gas. You need to find the mass of 2 moles of ammonia gas. Just let's find the mass of 1 mole of ammonia first, right? Nitrogen 14 plus hydrogen 3 equal to 17 grams. 17 grams. Why I wrote 17 grams? Because it is asked about the moles. It is not about 1 atom of something. It's about mole, right? Whenever you're asked about the mass of some species in moles, you can definitely, surely write the unit in grams. Or else you need to write in AMU or U, unified mass. So this is the mass of 1 mole of ammonia. So to get 2 moles, just multiply it with 2. 17 into 2. Now, moving on to the next sub-question. Calculate the volume of 850 gram ammonia at STP. 850 gram ammonia at STP. So at STP, you need to know the equation to be used. That is, given volume divided by 22.4 liters equal to number of moles. This was the last equation we studied right now, right? Here, number of moles equal to volume of gas at STP divided by 22.4. The same equation is given here. Number of moles equal to given volume by 22.4 liters. Here volume isn't given, so how do we find the volume? Mass is given, right? Even number of moles is not given. So the mass is given here, 850 gram. So just do this. Given mass is 850 gram. Given mass divided by molar mass. What is the molar mass of ammonia? NH3? Yes, 17. So divide this. Let's see what the answer is. 50. Okay, it's 50. So the number of given mass by molar mass gives you the number of moles. So number of moles is given. 850 by 17 equal to 50. So we are asked to find the volume. What do we do? 50 into, say, we know the equation of finding the number of moles using volume. The number of moles of something is equal to given mass, given volume divided by 22.4 liters, right? You just have to multiply this with 22.4 liters and you'll get the answer, volume in liters. All right? Calculate the number of oxygen atoms in 5 moles of glucose. The equation for glucose is, the molecular formula of glucose is already given there. So C6H12O6. 1 molecule of glucose means how many oxygen atoms? 6 oxygen atoms, right? 1 mole molecule. 1 mole molecule of glucose. 1 mole means what? 1 mole Na, right? 1 mole molecule of, not glucose. 1 molecule of glucose contains, 1 molecule of glucose contains 6 oxygen atoms. 1 mole molecule of glucose contains 6 into Na oxygen atoms. The question is asked about number of oxygen atoms in 5 moles of glucose. So 5 moles of glucose means 6 into 5 into Na means 30 Na. 30 into 6.022 in 10 raised to 23. So just listen once again. 1 molecule of glucose means 6 oxygen atoms. 1 mole molecule of glucose means 6 into Na atoms, oxygen atoms. 5 moles of glucose means 6 into Na into 5. 5 6 are 30 Na. Calculate the molar mass of water, carbon dioxide and methane. H2O. H2O means 2 plus 16, right? 18 grams, gram per mole, 18 gram per mole. CO2, carbon 12 plus oxygen 16 into 2, 32. 32 plus 42, 44, 44 gram per mole. CH4, carbon 12 plus 4, oxygen, it is 4. 4 into 1, 4. Carbon 12. It is 16 gram per mole. 18 gram per mole, 44 gram per mole, 16 gram per mole. It's just very simple question, right? Write the postulates of Dalton's atomic theory. I've already discussed the Dalton's atomic theory in previous part. Just listen to it. Around 4 to 5 postulates are there from Dalton's atomic theory. Which is heavier, 1 oxygen atom or 10 hydrogen atoms? Which is heavier, 1 oxygen atom or 10 hydrogen atoms? As it is asked about 1 atom, we can surely write it as 1 oxygen atom, the mass is 16U. 10 hydrogen atoms, the mass is 10U. The mass of 1 hydrogen atom into 10. That is 1U into 10, 10U. So just look to it, 16U or 10U is heavier. Obviously 16U, that is for oxygen atom. Calculate the number of moles in 1 liter of water. Calculate the number of moles in 1 liter of water. So the density is given here. I'll change the color. density is given here. Density 1 gram per milliliter. 1 gram per milliliter. I need to convert this to kilogram per liter. Kilogram per liter. For that, 1 liter contains 1000 grams or 1 kilogram of water. Let it be like that. So, just in order to find the number of moles here, just divide the given mass by molar mass. How will we do that? The given mass is 1000 divided by the molar mass 18. 18 for water, H2O, 18. You'll find the answer here. That will be the number of moles. We also need to find the number of water molecules in 1 liter of water. Water molecules. If you have the number of moles, just multiply with the Avogadro number and you'll get the number of molecules. So this answer into Avogadro number Na will give you the number of water molecules in 1 liter of water. Alright? What is atomic mass unit? What is atomic mass unit? It is 1 by 12th mass of C12 atom or C12 isotope. I've told you the story of isotope, the C12 isotope, the unified mass, the atomic mass unit in detail. So it will be easy for you. Just when it asked about the atomic mass unit, just tell it it is a 1 by 12th mass of C12 atom. It is expressed in AMU or U, which is unified mass. How many moles of dioxygen are present in 64 grams of dioxygen? What is dioxygen? O2. So what is the mass of O2? 32 grams, which means 16 into 2 gives 32 grams. We are asked to find the number of moles of dioxygen present in 64 grams of dioxygen. The given mass is 64 divided by the molar mass gives 2 moles. The molar mass of dioxygen is 32. The given mass is 64. Alright. Which of the following contains maximum number of molecules? Maximum number of molecules. So, molecules, the number of molecules. The number of molecules is directly proportional to number of moles. Right? Number of moles. The number of moles is directly proportional to what? Given mass by molar mass. Number of moles is given mass by molar mass. So we can say that it is inversely proportional to molar mass or atomic mass of something. Right? It is inversely proportional to atomic mass or it is inversely proportional to the molecular mass. Hope you understood the relation. Number of molecules means the number of molecules of a substance means it is directly proportional to number of moles. Because in the previous question here, we are asked to find the number of water molecules in the sub-question B. So what I have done is, I've first found out the number of moles of water molecules, the number of moles of water, and I've just multiplied it with Avogadro number so that I'll get the number of molecules. So the number of moles into Avogadro number gives you the number of molecules. So we can surely say that the number of molecules is directly proportional to number of moles. Number of moles is inversely proportional to atomic mass or molecular mass. So in the question provided here, you don't have to go in detail like counting, like calculating the mass of N2 separately, calculating the mass of CO2, calculating the number of moles molecules in H2, calculating the number of molecules in NH3. Don't waste your time doing all those. From this relation, we can easily say which one has the highest number of molecules. The one having lowest molar mass will be having highest number of molecules. So see, we are provided with 1 gram of N2, CO2, H2, NH3. So which is having the lowest molar mass? Lowest molar mass. Is it N2, CO2 or H2 or NH3? Definitely H2. 1 gram H2 has lowest molar mass, hence it will be having highest number of molecules or number of molecules. We're going to take a new topic from the Some Basic Concepts of Chemistry, a very easy topic. Actually, the title of the topic is percentage composition. Percentage composition, or it can be called as mass percentage. Mass percentage. What is mass percentage or the percentage composition? Percentage composition means it is a composition of any one element or component of a substance expressed in percentage. I'll explain it in detail using an example. We are provided with CO2, right? CO2. What is the mass of carbon? 12. What is the mass of oxygen? Yes, O2, 32. And the total mass is 44 grams. Now, my requirement is to find the mass percentage of carbon in CO2, which means I need to find the percentage of carbon in CO2. How much percentage of CO2 is carbon? I need to find how much percentage of CO2 is carbon. So for that, what I have to do is mass of carbon divided by total mass of CO2 into 100 percentage. This will give me the mass percentage of carbon, which means mass of carbon is 12. The total mass of CO2 is 44 into 100% will give me the mass percentage of carbon in CO2. Now, I need to find the mass percentage of oxygen. What I have to do is the mass of oxygen is 32 divided by mass of CO2 44 into 100 percentage. This will give me the mass percentage of oxygen in CO2. So now, hopefully, right? Are you clear? Are you ready with this topic? Are you okay with this topic? Is it okay? Mass percentage of something means what? It is a mass of that component, the percentage of mass of that component to the total mass of the substance. There's a question provided here. Calculate the mass percent of different elements present in sodium sulfate. Sodium sulfate, the molecular formula is given here. Na2 sulfur SO4. Okay. So I need to find the mass percent of Na2 sulfur O4 in Na2SO4. What do I have to do is Na2, what is the mass of Na2? 23 into 2. 23 means it is the mass of Na atom, right? So 23 into 2 means 46 given mass divided by the molar mass of the substance. The molar mass is, we need to calculate, right? Na2 is 46 plus sulfur 32 plus oxygen 16 into 4, 142 into 100%. This will give you the mass percentage of Na2 in Na2SO4. In the case of sulfur, given the mass of sulfur in Na2SO4 is 32 divided by the total mass of the substance 142 into 100%. All right. In the case of oxygen, the mass of O4 in Na2SO4 is 64 grams. Oxygen 16, right? 16 into 4 is 64 divided by 142. 142 means the total mass of Na2SO4 into 100% will give you the mass percentage of O4 in that particular substance. Now we are going to learn what is molecular formula and what is empirical formula. You're thorough with the word molecular formula because you are familiarized with the term molecular formula from standard 8 onwards, right? So you know what molecular formula is. Then what is empirical formula? Molecular formula means a formula that gives you the atoms present in a substance, also the number of atoms of that substance. For example, I'm taking water, H2O. Okay, H2O is a molecular formula of water. So when I look at this equation, the formula here, this is a molecular formula. What info can I get from this molecular formula? From molecular formula, you'll get to know the atoms present in a compound and also the number of atoms in a compound. When I look at this formula, the molecular formula of water, I can understand that hydrogen and oxygen are present in water. Okay. Also, I can understand that there are 2 hydrogen atoms and 1 oxygen atom in water. So molecular formula is a formula that will give you the exact number of atoms present in a compound. Also, you'll get to know what all atoms are present in a compound from molecular formula. Coming to empirical formula. From empirical formula, you'll understand what all atoms are present in a compound, but you'll never know the exact number of atoms present in a compound. But rather, you'll get to know a whole number ratio of the atoms present in a compound. Alright, from empirical formula, you'll never know the exact number of atoms in a compound, but just you'll get to know the whole number ratio of the atoms present in a compound. Let's do a few problems. C6H12O6. Molecular formula of what? Glucose. So while looking at this molecular formula, I can easily understand that glucose contains carbon, hydrogen, oxygen. Also, there are 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms in glucose. While coming to its molecular formula, you just have to divide the number of atoms with a simple whole number. Okay, you'll get simple whole number ratio. I'm dividing it by 6, hence I'll get CH2O. Dividing the number of atoms with a simple whole number, that is 6. I've taken 6, so I got the simplest whole number ratio, or the empirical formula CH2O. CH2O is the empirical formula of the glucose, which has molecular formula C6H12O6. Coming to H2O2, hydrogen peroxide. Looking at hydrogen peroxide, it is a molecular formula. I can understand that there are hydrogen and oxygen in hydrogen peroxide, and also there are 2 hydrogen atoms and 2 oxygen atoms. Coming to the empirical formula, I have to divide it by a simple whole number. I'm dividing it by 2. Hence, I get HO, which is the empirical formula. Empirical formula. Coming to CO2, carbon dioxide. CO2. Carbon dioxide has 1 carbon atom and 2 oxygen atoms. Okay, carbon dioxide is made up of carbon and oxygen. I know that. It's a molecular formula. What will be the empirical formula of CO2? Is it possible to divide the number of atoms of carbon dioxide by a simple whole number? No, it's not. We can't divide carbon dioxide and atoms present in carbon dioxide with a simple whole number ratio. So the molecular empirical formula and molecular formula of carbon dioxide is same, CO2 itself. There are some compounds having similar property, having molecular formula and empirical formula same. Okay, CO2 is one such compound. And now, in order to do the problems coming from the empirical formula section, molecular formula section, you need to know these equations. Empirical formula into N gives molecular formula. In the previous case, we have learned that CH2O is the empirical formula of glucose. Okay, I know the empirical formula of CH2O. How will I reach the molecular formula? In order to reach the molecular formula, you need to know N. I know N is equal to 6. N is equal to 6. So how will I reach the molecular formula? I've been given with the empirical formula. I know the N value also. How will you reach the molecular formula? Just multiply the empirical formula with N. That means C6. H2 into 6 gives 12. O 1 into 6 means 6. So this is the molecular formula of glucose. It has been... Okay, I've got it from the equation EF into N equal to MF. MF means molecular formula. EF means empirical formula. So if you know the EF and if you know the N value, the whole number, just multiply it and you'll get the molecular formula. Similarly, in order to get the N value, whole number, you have to divide the molecular mass by empirical formula mass. Okay, what does empirical formula means? Just summing up the masses of each element present in the empirical formula. Okay, so if you have the molecular mass and empirical formula mass, divide it and you'll get N value. In every question, you'll be provided with the molecular mass. In some cases, you need to find the empirical formula mass. In some cases, you need to find the whole number and also the empirical formula or the molecular formula. Okay, numerical problems will come as such. So if you have the n value and the empirical formula, just multiply it and you'll get the molecular formula. If you don't have n value, but you have the molecular mass and empirical formula mass, just divide it and you'll get the n value. All right. The problems regarding this session, this topic will be done in the next part. See you then. Bye.